Good evening, dear students. Today we'll be starting the sediment hydraulics. Okay, sediment hydraulics involves how the sediments are getting transported, how they are getting transported, and if they are getting deposited, why they are getting deposited, and once deposited again, if you want to retransport the sediments, what do you need? Okay, so these all things will be covered under sediment hydraulics. So first of all, we will see that we are here considering only the river condition. Okay, there are other environments where the sediments are getting transported, like wind environment is there, ocean environment is there, then groundwater environment is there, very finer sediments, ionic particles, they are getting transported. Then hill slope environment is there. Okay, automatically due to a landslide or slow rock creep or dust particles are falling, and so many things are there, but we are here focusing on the river. Okay, so river, sediment transports in river. So water discharge of a river, what will be the water discharge in a river? If the water discharge is q, then width of the river into multiplied by the depth, so it will be giving us the area. So that means if the river is flowing like this, and if the river is flowing like this, and this is the width, this is the width of the river, and this is the depth of the river, it will give us the area through which the water is flowing, or the basinal area of the river, cross sectional area, we can say cross sectional area. Then v equal to velocity of the water which is flowing inside it. So width of the area, width of the river is w, d is equal to depth of the river, v equal to velocity of the flowing water. So discharge is always measured for a particular location. That means suppose a river is coming from here to here, here discharge will be different, 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 and here the discharge will be different. So one more thing, discharge is measured at a particular time also. Here at 1 pm discharge is different, at 2 pm the discharge may be different if the rain, more and rain will be there in the ऑपोजिट डायरेक्शन, बिकॉज रिवर इज फ्लोइंग लाइक दिस. सो इफ यहाँ पे अगर रेन हो जाएगा तो यहाँ पे 2 PM को डिस्चार्ज बढ़ जाएगा. ओके, सो दिस इज द थिंग. सो डिस्चार्ज इज ऑलवेज मेजर्ड फॉर ए पर्टिकुलर लोकेशन. WD जो मैं जो बोला, दिस इज द विड्थ एंड दिस इज द डेप्थ. So it will give us a cross sectional area, it will give us the cross sectional area. So we can write that these two terms we can convert into the cross sectional area into velocity. Okay, this is the amount of discharge of water. So hydraulic radius of the river, this is very important. So suppose the depth of the river is like this, and this is the side walls of the river, these are the side walls of the river, and where you are having your trees, you are having the grass, again this side you are having the grass. Okay, but every time what is happening, water is not flowing up to this, na, water may flow up to this, water may flow up to this, may flow up to this, may flow up to this. Suppose during the flood condition, water may flow up to this condition. During after the flood, it may reduce up to here. During the winter, water may flow up to this condition, and during the summer this may flow up to here. So the water condition, flowing water condition, the height or the depth of the water which is flowing, that varies season to season, month to month, and day to day. So what is hydraulic radius? The height up to which the water is available in the river, and from there you have to see the width. Okay, here you will not see this width, you will not see this width, you will be seeing. Okay, up to which the water is available. So this is the hydraulic radius, or this is the cross sectional area, that is the active cross sectional area, we can say, through which the water is flowing. We will not calculate the cross sectional area up to here. Once we will call the hydraulic radius, this is actually the hydraulic radius, this is the hydraulic radius from this point to this point, this is the hydraulic radius, ABC. This is the hydraulic, it is calculated by comparing the weighted perimeter. We can say up to here water is flowing, na, this is weight, this portion is weight. Okay, water is going like this is weight, ना, this यहाँ पे जो ज़मीन होगा, रिवर का बेड जो होगा वो वेट है, बट यहाँ पे जो रिवर का बेड होगा वो तो वेट नहीं है ना, वेट है मतलब भीगा हुआ है. ठीक है. सो द weighted perimeter of the cross sectional area of the river. So that means what I am trying to do, up to which the water is present there. This is the depth we will calculate, this is the width we will be taking, and this will give us the actual cross sectional area, and with this we have to multiply the velocity of the river, which will be giving us the Q discharge. Okay, but Q here, whatever I told you, this is the maximum discharge capacity of the river, but here the Q is the actual discharge capacity at a particular time. Okay, so right now we will be moving into so many formulas, so that we can easily understand these things in a better way. So we will be discussing what are the types of the flows and how, which one is controlling the type of the flow, that means the width is controlling, or the depth is controlling, or the gradient is controlling, or the velocity of the water is controlling. We will be seeing all these things. So now first we will be so viscosity generally the unit is centipoise we say. At 20 degree centigrade 1 centipoise the viscosity, and temperature if you will increase, then viscosity will be decreasing, na, you know all. So at 25 degree the viscosity is this much centipoise of the water. Okay, generally. So we will be right now moving into Reynolds number. This is R is equal to V into L by V. So what is happening? So here V is equal to velocity, this is the velocity, this is L. L means linear measurement, like depth we can take, or we can take the hydraulic radius of the channel. We can either take this depth we can take, or we can say the hydraulic radius of the channel, this one, hydraulic radius of the channel. So V L can be anything. So V equal to kinematic viscosity of the fluid. Kinematic viscosity is equal to, you all have read in physics that coefficient of viscosity, that is mu divided by rho. Okay, so coefficient of viscosity divided by rho means density. So coefficient of the viscosity divided by density will give you the kinematic viscosity, or V. Okay, so the thing is that what I am trying to do, the Reynolds number equal to this one. Okay, we will be keeping this upper portion same, but this kinematic viscosity we will be keeping this term, this by this. So finally the Reynolds number will become this. Okay, so V into L, any linear parameter like depth of the channel, hydraulic radius of the channel, and rho, density divided by the mu. Mu is the coefficient of viscosity. Okay, if you are having the data of these three data, then you can find the Reynolds number. If you are having these three data, like this you are having, this you are having, again this you are having, then you can easily find the Reynolds number. So Reynolds number will decide whether the flow will be lamellar flow or it is a turbulent flow. So what is a lamellar flow and what is a turbulent flow? That picture should be in our mind, otherwise there will be no use of Reynolds number. So let's see. So here I have explained this formula in elaborate way. So this is the velocity into linear parameter into density of the water divided by the coefficient of viscosity. Okay, so velocity into depth of initially what was that? Velocity into depth or hydraulic radius divided by kinematic viscosity. Later on kinematic viscosity we are replacing by coefficient of viscosity by density. So it will be, density will be going up because it is there down in the denominator, so it will be going into numerator. So this is the formula, this is the final formula, or we can say this formula is equal to mu into V into L into density divided by coefficient of viscosity. Okay, this is the Reynolds number. And the thing is that there are actually two types of flow, as I have told you, that Reynolds number decides whether the flow in the channel will be lamellar flow or turbulent flow. So due to this we will be discussing what is the two types of flow. One is lamellar flow and another one is turbulent flow. Okay, so the thing is that the thing is that these two things they are dependent upon the resistance offered by the viscosity of the medium. Viscosity जो होगा medium का वो कितना resistance offer करता है. Viscosity is the opposite to fluidity ना. Viscosity means resistance to flow. Viscosity means the resistance to flow. So we will see how the resistance is there. Viscosity resistance is there in the flow, then flow velocity. So these are the two things which will be deciding whether the flow is lamellar or turbulent flow. So you see, in case this is the lamellar flow and this is the turbulent flow, I will be discussing one by one. So you see, this is suppose one particle, at 6:25 p.m. At 7 p.m. it will be here. At 8 p.m. it will be here. At 10 p.m. it will be here. In a straight line it is moving. So every second the particle is moving in this direction only. This particle is moving in this direction only, and this particle is moving in this direction, and this particle is moving in this direction. But in case of the lamellar flow, what is happening? The thing is that the thing in case of the lamellar flow, that means we can say the direction of the movement is not changing for a particular particle. So every particle they are moving a very smooth direction, or that they are not changing the direction. But in case of the turbulent flow, if you will see, so if you will see this particle, it is changing continuously its direction of travel. You will see this particle, na, this is continuously changing its direction of travel. You see, they are continuously changing. So at any moment you cannot decide the flow direction, but overall the flow direction is this direction. That means overall this particle will be finally carried in this direction, but it is not carried in a straight way, straight manner. It will be carried like this, like this, like this, like this. Okay, this is the movement direction. So it is continuously every second it is changing. If you mark one particle, na, if you mark this particle, it is moving in like this, again like this, again like this. If you mark this particle, again moving like this, moving like this, like this. Okay, so these are the conditions. These are the basic difference between lamellar flow and turbulent flow. In case of the lamellar flow, what is happening? If you will take two examples, the paint, you are having a paint and you are having the water. So paint में viscosity बहुत ज़्यादा होता है, मतलब ये resist करता है flow के लिए, so it will be flowing like this, lamellar flow. Okay, but if will be marking the water, इसमें viscosity तो कम होता है, the flow will be turbulent flow. In between two, but there are water bodies where the lamellar flows are also present. I will be telling all about them. Okay, so flow velocity यहाँ पे कम होता है, paint अगर flow होगा, flow velocity कम होगा, as the viscosity is very high and flow velocity is very कम, it will be lamellar flow. But here flow velocity जब ज़्यादा हो जाता है water में in comparison to paint, so यहाँ पे viscosity भी कम हो जाता है in comparison to the paint, so it will be a turbulent flow. These are the best examples. So lamellar flow कब होता है ना, जब resistance offered by the viscosity of the medium is greater than the flow velocity of the medium. So that means we can say the flow velocity is lower and the resistance offered by the viscosity of medium is higher. Then only in that condition the lamellar flow is possible. Okay, but which number will give us the idea about the lamellar flow or turbulent flow? So last page we discussed that Reynolds number will be giving us the idea about the whether the flow is lamellar or whether the flow is turbulent. Okay, so again we are rediscussing the Reynolds number, and there is nothing nothing to rediscuss. But here you see, we have already discussed, but this portion, when the Reynolds number is less than 500, then the flow is lamellar. Okay, if the Reynolds number is less than 500, then the flow is lamellar, and if the Reynolds number is greater than 200, the flow is turbulent, and if it is in between 500 to 200, then the flow is in a transitional zone. That means mixture of lamellar and turbulent. So the thing is that so in two things the Reynolds number are getting generally decided. One is viscosity of the fluid we decide, and the gravity कितना है, मतलब water जो flow हो रहा है उसको gravity कितना pull कर रहा है. So these are the also two things which are also playing important role. Now we will be seeing how the Reynolds number is becoming less than 500 and how it is becoming greater than 2000. Okay, I was just about to tell 2000 rupees. Okay, so 500 कब होता है हम देखेंगे अभी, एंड 2000 से ज़्यादा कब होता है देखेंगे. 500 से नीचे कैसे होता है, 2000 से ज़्यादा कैसे होता है हम देखेंगे. सो these are the bigger pictures of the lamellar flow and turbulent flow. So here the Reynolds number is less than 5. So if you mark, there are 4 particles, pathway of 4 particles, 1, 2, 3 and 4 are there. Every time they are moving in single straight direction. Every time they are moving in a straight direction. Every time whenever you see, they are moving in a straight direction. But in case of these turbulent flow, they are moving in haphazard direction. That means they don't have a particular direction for a longer period of time. Every point of time they are changing their direction, but finally they are flowing in this direction only. Finally, if you will put a particle here, you will get the particle here, but it will moving like this, like this, like this and here. So Reynolds number depends upon the inertial force. Inertia का force क्या होता है, उस पे डिपेंड करता है, एंड द विस्कस फोर्स, विस्कोसिटी ऑफ द मीडियम पे डिपेंड करता है. सो इनर्शियल जो फोर्स होता है दैट एक्सीलरेट्स द फ्लूइड फ्लो, एंड विस्कस फोर्स क्या होता है, रेजिस्ट द फ्लूइड फ्लो. ओके, सो इनर्शियल फोर्स जो होता है दैट एक्सीलरेट्स द फ्लूइड फ्लो, वेयर एज द रेजिस्टेंस कौन देता है ना, विस्कस फोर्स जो होता है वो रेजिस्टेंस देता है. इफ विल सी दैट रेनॉल्ड्स नंबर इज दिस मच ना, द फॉर्मूला इज दिस. सो रेनॉल्ड्स नंबर इज डायरेक्टली प्रोपोर्शनल टू द वेलोसिटी. वेलोसिटी अगर बढ़ेगा तो रेनॉल्ड्स नंबर का वैल्यू ज़्यादा आएगा. अगर विड्थ या डेप्थ बढ़ता है और या हाइड्रोलिक रेडियस बढ़ता है देन रेनॉल्ड्स नंबर ज़्यादा आएगा. इफ़ द डेंसिटी बढ़ता है तो रेनॉल्ड्स नंबर ज़्यादा आएगा. if the coefficient of viscosity, this is the coefficient of viscosity, if that is increasing then the Reynolds number will be decreasing, because Reynolds number is inversely proportional to coefficient of viscosity. This is the coefficient of the viscosity. So generally we call it viscosity is. So if the viscosity is increasing, the Reynolds number will be decreasing. Okay, and the flow will be lamellar. Okay, so that means what I am trying to tell you, the more the viscous the medium will be, the more the viscous the liquid will be, the Reynolds number will be less, because Reynolds number is inversely proportional to viscosity. Okay, so this is the thing. So this is the diagram where we can see, this is the diagram between the depth of the water, again the velocity of the flow, and we can see that here this line is 500 for the medium, Reynolds number 500 for the medium, this line. And if the medium will be at 20 degree, sorry, if the medium is at 20 degree, and if the medium is at 0 degree, then this is this 0 degree में होने से क्या होगा, विस्कोसिटी जो होगा और भी बढ़ जाएगा. तो लाइन यहाँ से यहाँ तक शिफ्ट हो जाएगा. अगेन दिस इज द 2000 लाइन. सो 500 के नीचे जो भी होगा, दिस रीजन विल बी गेटिंग लैमेलर फ्लो, एंड 2000 के ऊपर जो भी होगा इन दिस रीजन विल बी गेटिंग टर्बुलेंट फ्लो. एंड दिस इज राइट नाउ डोंट फोकस ऑन दिस इज द फ्रॉड नंबर विल बी डिस्कसिंग इन द नेक्स्ट क्लास. So here what is happening, at 0 degree the Reynolds number less than 5 as viscosity increases. 0 में viscosity increase होगा. Remember, जितना ठंडा होगा मीडियम उतना viscosity increase होगा. Okay, जितना ठंडा होगा उतना viscosity increase होगा. You just see, you cool a already melted chocolate, that will try to get re-solidified. Okay, that means viscosity increase होता है. So यहाँ पे क्या होता है, at 0 degree, so the Reynolds number line will be here, और at 20 degree हाँ, अगर विस्कोसिटी इंक्रीज हो गया, अगर 30 डिग्री का लोगे तो कहाँ पे होगा रेनॉल्ड्स नंबर लाइन, यहाँ पे हो जाएगा. 20 डिग्री में यहाँ पे, 30 डिग्री यहाँ पे होगा, क्योंकि वहाँ पे विस्कोसिटी डिक्रीज हो जाएगा. So the thing is that what I am trying to tell you, so this is the finalized view, that when the temperature is at 20 degree, the Reynolds number line 500 line is here, and if we are decreasing the temperature up to 0 degree, then line is shifting because the viscosity is increasing, and below 500 up to here we can consider the lamellar flow, and above 500 to 2000 will be considered into transitional flow, and above 2000 will be considered into turbulent flow. So here I have written clearly, you can have a note from this also. You will, every time you have to pause the video and you make your own note. Okay, when we increase the temperature of the medium, then what is happening, the flow viscosity decreases and the result in increase in Reynolds number, which will lead the flow to, which will lead to convert the flow from turbulent to, from lamellar to turbulent, and with increasing temperature a lamellar flow will be converted into transitional flow or turbulent flow. So यही मैं बोल रहा था. ओके, बस टेम्परेचर इंक्रीज होने से नहीं होता है, द वेलोसिटी ऑफ द मीडियम, इंक्रीजिंग वेलोसिटी ऑफ मीडियम इज ऑल्सो नीडेड. ओके, so finally क्या होगा, with increasing temperature viscosity decreases and Reynolds number is inversely proportional to viscosity. So viscosity अगर डिक्रीज होगा, Reynolds number इंक्रीज होगा. So density of water जब इंक्रीज होगा and density of water जब इंक्रीज होगा, Reynolds number बढ़ेगा. रेनॉल्ड्स नंबर इज डायरेक्टली प्रोपोर्शनल टू डेंसिटी एंड डेंसिटी बढ़ेगा तो रेनॉल्ड्स नंबर बढ़ेगा. दिस इज व्हाट आई एम ट्राइंग टू टेल यू. सो देन कम्स द फ्रॉड नंबर. सो रेनॉल्ड्स नंबर इज ऑपरेटेड on the basis of inertial force. This is very important. You see Reynolds number formula is all right, but inertial force is important and viscous force is important. So what is the work of the inertial force? Inertial force का काम ये है कि accelerates the fluid flow, and here viscous force का क्या है कि रेजिस्ट द फ्लूइड टू फ्लो, मतलब फ्लो नहीं करूँगा मैं यहीं पे रुकूंगा विस्कोसिटी अगर ज़्यादा है. ठीक है. सो नाउ विल बी मूविंग इनटू द फ्रॉड नंबर. ओके, फ्रॉड नंबर क्या कहता है? एफ इज इक्वल टू वी डिवाइडेड बाई जी इंटू डी. हियर जी इज इक्वल टू acceleration due to gravity and d is equal to depth. D is equal to depth and f equal to forward number and v equal to velocity of the medium. It is much simpler than in comparison to the Reynolds number. So here what is happening? Acceleration of due to gravity we are taking 9.8 meter per second square, and the Froude number determines whether the flow will be tranquil. That means whether it is a calm flow और शांत हिसाब से पूरा धीरे धीरे बह रहा है, और इट विल बी ए रैपिड और स्ट्रीम जैसा, मतलब वाटरफॉल जैसा बहुत ज़ोर से बह रहा है. ठीक है. इट विल डिसाइड इट इज़ ए ट्रैंक्विल और इट इज़ ए रैपिड. ओके, सो एग्जांपल हम एक ले लेंगे. सो फ्रॉड नंबर तो है एफ इक्वल टू वी डिवाइडेड बाई जी डी होल रूट ओवर. सो हियर सपोज द वेलोसिटी ऑफ द फ्लो इज 10 किलोमीटर पर आवर एंड 50 meter depth is there. Okay, 50 meter depth. Okay, so here 10 kilometer per hour velocity is low ना, and depth is high. तो velocity अगर low होता है, depth अगर ज़्यादा होता है, तो definitely this portion is lower, this portion is higher. So definitely Froude number will be less than 1. So if the Froude number is less than the 1, this is known as the subcritical flow or tranquil flow. Okay, so when the Froude number is less than 1, it is called lower flow regime. Okay, you remember it. When the Froude number is less than 1, it is called the lower flow regime, and this is also known as the subcritical flow or tranquil flow. So lower flow regime में subcritical flow और tranquil flow होता है. So जब क्या होता है ना, if the velocity is low and the depth is high, okay, gravity remains same na, gravity remains same. If the velocity low and depth is high, this only happens. Less than 1 the Froude number value. And in one condition, second condition will say, let's take the velocity very high, whereas depth is 10 meter only. So definitely here the numerator is high in comparison to denominator, so definitely the f value will be greater than 1. So this is known as upper flow regime. We can say this is the supercritical flow और known as the rapid. So this kind of flow will generate rapid flow. So कि कब होता है? जब velocity बहुत ज़्यादा होता है in comparison to the flow depth. So क्या होगा? पानी बहुत ज़ोर से निकलेगा. ओके, पानी बहुत ज़ोर से उस जो एरिया है पानी निकलने के लिए, जो बेसिनल एरिया है उसमें बहुत ज़ोर से निकलेगा, तेज़ी से निकलेगा, तो फ्रॉड नंबर 1 से ज़्यादा हो जाएगा. एंड दैट तेज़ी से पानी निकलने के लिए हम क्या बोलते हैं? रैपिड बोलते हैं. सो ओके, सो इफ दिस एंड दिस विल बी सेम, this is x in any condition, this is x, then this is 1. This is known as the critical flow, which is very rare. In nature you won't find any kind of critical flow. Okay, so right now what I am telling you, I am giving you just one example. You can easily understand where the rapid is taking place and where the tranquil flow is taking place. You just consider this is one dam. Okay, you just consider this is one dam and this is the flow direction of the river. So dam is there, so पानी किस तरफ जमा होगा? इस तरफ ना, नो, इस तरफ कैसे जमा होगा? अपस्ट्रीम में जमा होगा. ओके, अपस्ट्रीम में पानी जमा होगा, यहाँ पे पानी जमा होगा. सो व्हाट एवर द वाटर विल कम ना, हियर यू सी डेप्थ इज वेरी हाई एंड आज ऑब्स्टेकल इज देयर, द डैम इज द बैरियर. सो वाटर का वेलोसिटी धीरे होगा, यहाँ पे पानी का वेलोसिटी धीरे होगा और यहाँ पे पूरा जीरो हो जाएगा पानी का वेलोसिटी. तो यहाँ पे रोक दिया ना वो जो ऑब्स्टेकल है. सो हियर क्या हुआ ना, डेप्थ इज वेरी हाई, वेलोसिटी इज वेरी लो, एंड डेफिनेटली द फ्रॉड नंबर विल बी लेस देन 1. So like this, the Froude number will be less than 1. So it will be a lower flow regime or subcritical flow. Okay, but once the gate opens, gate जब नीचे से खुल जाता है, गेट तो ऐसे हम लोग दरवाजा जैसे ऐसे नहीं खोल देते हैं, धीरे धीरे ऊपर उठाते हैं गेट को. तो यहाँ से जब पानी निकलेगा तो यहाँ पे क्या होगा, वेलोसिटी इज़ वेरी हाई. जब पानी निकलता है ऐसे इतना हाइट में तो पानी नहीं निकलेगा, तो कम हाइट में पानी निकलेगा. तो बहुत ज़ोर से पानी निकलेगा। क्यों? यहाँ पे रास्ता जो है पानी निकलने के लिए इस तरफ कम है, ये जो रोड है, ये सॉरी पानी निकलने के लिए जो रास्ता है इस तरफ ये कम है। सो व्हाट विल हैपन? सो मच अमाउंट ऑफ वाटर विल बी moving through this small space which is provided by lifting the barrier or lifting the gate of the dam. So it will lead to a very high flow velocity. Okay, but यहाँ पे जो पानी निकलेगा इसका तो डेप्थ कम है, so यहाँ पे क्या हुआ, डेप्थ इज वेरी लेस, flow velocity is very high because suddenly the water is getting released. So here front number is much greater than 1, so this flow will be a rapid, whereas this flow this side will be a tranquil flow. Okay, so this is the condition. Okay, so this is the condition that when the flow velocity is very high and the depth is low, so then that time the rapid will be taking place, and when the flow velocity is low and the depth is very high, then that time the tranquil flow will be taking place. This is the example I gave you because in this example you will be having two conditions at a time simultaneously. Okay, so you try to travel one barrage or any gate or any gate, you can easily see that in the upstream direction the flow is very calm, whereas in this direction the flow is very fast. Okay, so this is the thing. Then we will be moving into the same thing that when velocity is low, depth is high, flow is less than 1, this is subcritical flow or known as tranquil flow, that is the lower flow regime, and F is equal to V by GD, and in case 2 V, this is D and this is D, and if the flow velocity is greater than 1, sorry, if the flow velocity is high and depth is low, the front number F will be greater than 1. This is the supercritical flow or upper flow regime flow. This leads to the formation of rapid. This is the summary that whatever we read, and this is the F equal to 1, which is very rare because this and this should be equal, and this is very rare. Okay, so this is known as the critical flow. Below less than 1, that is subcritical flow, greater than 1 supercritical flow, 1 critical flow. Okay, so these are the things. Then we will be coming into Bernoulli's equation. Okay, then we will be coming into Bernoulli's equation, and we will be discussing what is that Bernoulli's equation. Okay, that Bernoulli's equation, suppose on a ground or river bed, the one particle is there. Okay, so water is flowing. Okay, water is flowing, the velocity of water is getting putting some impact on this particle, whether it will move or stay. Again there is some pressure on the particle के ऊपर भी कुछ प्रेशर होता है, ठीक है. सो टोटल एनर्जी दिस इज द प्रेशर, टोटल एनर्जी ऑफ द ऑन द पार्टिकल क्या होता है, रो जी एच. ये तो पोटेंशियल एनर्जी हो गया, पार्टिकल जितना ज़्यादा हाइट में होगा तो उसके ऊपर डिपेंड करके पोटेंशियल एनर्जी है, और दिस इज द काइनेटिक एनर्जी एंड दिस इज द प्रेशर विच आई हैव टोल्ड यू, एंड दिस इज द काइनेटिक एनर्जी. ये जो काइनेटिक एनर्जी है फ्लो का, दिस इज द काइनेटिक एनर्जी एंड दिस इज द प्रेशर अबव द पार्टिकल, बिकॉज इसके ऊपर भी वाटर है ना, तो इतना प्रेशर है. सो पोटेंशियल एनर्जी हो गया दिस, काइनेटिक एनर्जी हो गया दिस, एंड प्रेशर हो गया टॉप से दिस. ओके, सो ये तीनों एक पार्टिकल के ऊपर है, एंड एनर्जी इज कंजर्वेशन अकॉर्डिंग टू लॉ ऑफ कंजर्वेशन ऑफ एनर्जी इज ऑलवेज अ कांस्टेंट. ओके, सो ये तीनों मिला के जितना है टोटल एनर्जी है, तो इसको मैं लिख सकता हूँ क्या, ये टोटल एनर्जी मैं लिख सकता हूँ, टोटल एनर्जी इज ऑलवेज ए कांस्टेंट. ओके, टोटल एनर्जी इज ऑलवेज ए कांस्टेंट. सपोज यू सी, आई एम गिविंग यू एग्जांपल. सपोज रो जी एच इज 5, this one is kinetic energy is 15, and pressure on the particle, that energy is pressure is 20. Okay, these are the numbers. Suppose we are increasing the velocity, so rho gh will not be getting some impact ना, velocity के साथ इसका क्या लेना देना. ये तो जितना हाइट में रहेगा, अगर हाइट बढ़ा देंगे तो rho gh बढ़ेगा, अगर हाइट बढ़ा देंगे पार्टिकल का, तो हाइट तो नहीं बढ़ा रहे हैं, वेलोसिटी बस हम इंक्रीज कर रहे हैं. हम बस क्या कर रहे हैं, वेलोसिटी को इंक्रीज कर रहे हैं. इफ़ वी आर इंक्रीजिंग द वेलोसिटी तो दिस विल बी इम्पैक्टेड, दिस 15 विल बी टर्निंग इनटू 20. सो ये जो रो जी था ये तो कांस्टेंट रहेगा, इसका कुछ नहीं होगा. सो डेफिनेटली व्हाट विल हैपन, दिस प्रेशर व्हाट एवर वी आर हैविंग इनिशियली 20 ना, टू मेक्स दिस एनर्जी टोटल 40, so this pressure will be reduced and it will be becoming 15. So that means what I am trying to tell you, whatever the pressure was there above the particle, so that pressure has been reduced. Okay, whatever the pressure was there above the particle, initially particle के ऊपर क्या कितना प्रेशर था, initially particle के ऊपर जो प्रेशर था वो था initially था 20, बट इनिशियली 20 था. अभी जैसे कि ये बढ़ गया और ये 15 बढ़ के 20 हो गया, 15 बढ़ के क्या हुआ 20 हो गया. सो ये जो प्रेशर 20 था ये प्रेशर 15 हो गया. तो प्रेशर हटा मीन्स द पार्टिकल विल बी ट्राइंग टू मूव लाइक दिस, इट विल बी लिफ्टेड ना. 20 में ये नीचे है, अगर प्रेशर कम हो जाएगा इट विल बी लिफ्टेड ना. तो लिफ्टेड होगा एट ए टाइम, ये फोर्स भी आ रहा है, काइनेटिक एनर्जी फ्लो भी हो रहा है, तो इस पार्टिकल को कैरी करेगा. So this Bernoulli's equation describes is known as the is known for generating the entrainment velocity. Entrainment velocity means the velocity, the minimum velocity we need to make a particle movement. Okay, this is known as bring into movement. So ये पार्टिकल तो रेस्ट में है, ये जो पार्टिकल है रेस्ट में है, इसको मूव करने के लिए जितना इनिशियल वेलोसिटी चाहिए दैट इज द एंट्रेनमेंट वेलोसिटी. And this is how the Bernoulli's equation deals. So total energy remains constant. If we are increasing the velocity, this will be impacted and this will be increased. It increased from 15 to 20. So this will be constant because we are not changing the height. These 5 remain constant. So who is going to change? This P 20 will be changing to 15. So this is 20 is getting reduced. So ये 5 बढ़ा 20 हो गया, ये 5 घट के 15 हो गया. So this is the condition. ठीक है, for the Bernoulli's equation. So here what is there? So this is the Bernoulli's equation, and the minimum velocity needed to initiate the movement for a already rested grain is called the entrainment velocity. मैं already बोल दिया हूँ. So we can say this bigger particle, this much smaller and smallest particle, so entrainment velocity will be different for the different particles. The bigger particles need more entrainment velocity, this needs more entrainment velocity in comparison to this, and this needs least entrainment velocity to get lifted. Okay, this needs least entrainment velocity to get lifted. Okay, so this is the thing that Bernoulli's equation explains or tells us about the entrainment velocity. मतलब एक grain that was in rest and we are trying to lift that grain. Okay, so then Bernoulli's equation that will help us. Okay, so in this Bernoulli's equation only the aeroplanes fly. Okay, you may search in some videos in YouTube and you can easily understand how the aeroplane is flying. So this is the thing. Then we'll be coming into settling velocity. हम तो ग्रेन को जो सेटल था उसको तो हम मूवमेंट करा दिए, लेकिन जो ग्रेन्स मूवमेंट में है देन हाउ टू सेटल दिस ग्रेन्स, व्हाट आर द नीडेड थिंग्स सो दैट द ग्रेन विल बी सेटल्ड. ओके, दैट इज नोन एज द रेस्टिंग वेलोसिटी. सो रेस्टिंग वेलोसिटी कितना होगा? सो ग्रेविटी इनटू डायमीटर ऑफ द ग्रेन इनटू डेंसिटी ऑफ द सॉलिड डिवाइड माइनस डेंसिटी ऑफ द फ्लूइड. सॉलिड जो है जो पार्टिकल है उसका डेंसिटी एंड फ्लूइड का डेंसिटी, उस दोनों को हम सब्सट्रैक्ट करेंगे डिवाइडेड बाय विस्कोसिटी 18 म्यू डिवाइडेड बाय 18 इंटू विस्कोसिटी. so this is the condition. so density of the particles, this is the velocity and this is the diameter of the grains. कितना बड़ा है, तो इसका मतलब क्या है, जो सेटलिंग वेलोसिटी है दैट इज डायरेक्टली प्रोपोर्शनल टू द डायमीटर. settling velocity is directly proportional to diameter. Gravity is constant na, and this is directly proportional to the contrast or difference between the densities, and it is inversely proportional to the viscosity. So what I am trying to tell you, bigger grains will be having wait a minute, हाँ velocity कितना होगा सेटल करने के लिए. सो यहाँ पे wait a minute, g into d into this, yes, formula is right, and then we'll see what is happening there. So it is called diameter of the grain. so diameter of grain जितना ज़्यादा होगा उसको, हाँ उसको wait a minute, v is equal to settling velocity, this is the density particles, acceleration due to gravity, mu equal to fluid viscosity equal to diameter of the grain. So v velocity कितना होगा, gravity से directly, diameter से directly, and density constant से भी directly. This is the density constant contrast between the solid and the fluid, and again this is inversely proportional to the viscosity, and acha, this is the condition that the particles, the bigger particles, if the particle is bigger na, we need higher velocity, in higher velocity the particle will be deposited. If the particle is smaller, this is v is directly proportional to d, means if the particle is very bigger, we need at very high velocity the particle will be deposited. But if the particle is very small na, we need to reduce the velocity to very smaller amount so that the particle will be deposited. इतना बड़ा पार्टिकल को डिपोजिट होने के लिए अगर 30 किलोमीटर पर आवर में फ्लो है, ये पार्टिकल डिपोजिट हो रहा है, ये 30 में डिपोजिट नहीं होगा, इसको डिपोजिट होने के लिए 15 किलोमीटर पर आवर चाहिए. अगर इससे भी छोटा पार्टिकल मैं ले लूँगा, इससे वाला, इसको डिपोजिट होने के लिए 2 किलोमीटर पर आवर जब वेलोसिटी होगा तब जाके ये डिपोजिशन होगा. ओके, दिस इज़ द कंडीशन, दिस इज द कंडीशन. ओके, जितना बड़ा पार्टिकल होगा वो दैट विल बी डिपोजिटेड एट अ हायर वेलोसिटी बिकॉज दैट इज हैविंग वेट, दैट इज हैविंग मोर ग्रेविटी. ओके, so this is the thing that so you see these particles, they will be deposited at higher velocity, this is much lower velocity, this is much lower, this is much lower, and these clay and silt particles na at velocity 0 kilometer पर सेकेंड पे डिपोजिट होगा. ये जो पार्टिकल है ना, जीरो होगा जब वेलोसिटी तब जाके डिपोजिट होगा, अदरवाइज दे विल बी सस्पेंडेड इन द फ्लो. ओके, सो देन कम्स द मोड्स ऑफ ट्रांसपोर्टेशन. सेडिमेंट तो हम पढ़ लिए, इतना तक 4 रूल्स हम पढ़ लिए, रेनॉल्ड्स नंबर, फ्रॉड नंबर, देन बर्नौली's equation, then Stokes law. Then we'll be into what are the modes of sediment transportation. Are the sediments flying, or they are rolling, or they are getting slided? What are the things we'll be discussing right now. Okay, so sediments actually transported in 3 conditions. One is bed load, that means on the bed, on the river, the bed load. Okay, then suspension load. Suppose water is there, this much amount of water is present, so here sediments will be transported. Then solution load in a ionic condition. So in water सोडियम का आयन है, क्लोरीन का आयन है, पोटेशियम, कैल्शियम, सबका आयन में है जो हमें नहीं दिखेगा. ओके, केमिकल एनालिसिस पे जाएगा. सो दीज आर द 3 कंडीशंस. बट द बेड लोड जो है, जो बेड के ऊपर होता है, सेडिमेंट ट्रांसपोर्टेशन होता है, एक ट्रैक्शन है और एक सल्टेशन है. ट्रैक्शन क्या है? सो ट्रैक्शन में क्या होता है, जनरली बेड लोड में बड़ा जो पार्टिकल है वो तो उनको तो वाटर ऐसे ही फ्लो करेगा, तो वाटर फ्लो हो रहा है उसको तो ऐसे नहीं रख पाएगा ना, इतना भी वेलोसिटी नहीं है. सो दे विल बी रोलिंग, और दे विल बी स्लाइडिंग, और दे विल बी फॉलिंग ओनली ऑन द सरफेस विदाउट एनी मूवमेंट. सो व्हाट इज हैपनिंग हियर? ट्रैक्शन एंड सॉल्टेशन एंड ट्रैक्शन क्या है? बेड लोड में हमारा जो पार्टिकल्स है, ग्रेवल साइज and coarse sand size particles, they will be traveling in the bed load. But the thing is that the gravel size, coarse sand size, and this depends upon the velocity. Sometimes the gravel size particle भी क्या होता है, बेड लोड में नहीं जाता है, ये कभी भी सस्पेंशन में ऐसे जाता है क्योंकि वेलोसिटी बहुत हाई होता है. ओके, so what I am trying to tell you, if the velocity is 10 km per hour, in second condition the velocity is 30 km per hour. Okay, coarse sand will be in suspension but gravel will be on the bed. सो कोर्स सैंड यहाँ पे 10 किलोमीटर में क्या होता है, कोर्स सैंड सस्पेंशन में चला जाता है. ओके, बट ग्रेवल जो होता है वो बेड में ही मूवमेंट करता है. बट इफ द 30 किलोमीटर वेलोसिटी इज देयर, हियर क्या होगा, ग्रेवल में स्टे इन सस्पेंशन, यहाँ पे ग्रेवल भी सस्पेंशन में जा सकता है. ठीक है, along with the sand. So sand, gravel दोनों velocity जब increase होगा दोनों suspension में जा सकता है. So depending upon the size and depending upon the velocity that we decide that whether it will be, the flow decides that whether it will be in bed load or whether it will be traveling in a suspended mode. Okay, so now we will be discussing about bed load. Okay, so bed load क्या होता है, एक traction होता है, एक saltation होता है. I have already discussed here traction here and written here, not discussed, sorry. So traction is there and saltation is there. So here what is happening in case of the traction, here traction, saltation. So boulder, cobble, pebble, granule and coarse sand and very coarse sand and coarse sand. Okay. So ट्रैक्शन में क्या होता है, तीन टाइप का, इधर रोल करके जा सकता है, अगर सर्कुलर पार्टिकल है तो रोल करके जाएगा, स्लाइडिंग करके जा सकता है, अगर फ्लैट ग्रेन है तो स्लाइड करके जाएगा, ऐसे ऐसे स्लाइड करके. एंड इम्पैक्ट एंड क्रीप एक होता है. इम्पैक्ट एंड क्रीप क्या होता है, इम्पैक्ट एंड क्रीप होता है क्या ना, एक ग्रेन आया पीछे से, इसको धक्का दिया तो ये थोड़ा खिसक गया, फिर ये जाके इसको धक्का देगा, ये थोड़ा खिसक जाएगा. Okay, that is known as impact and creep. But there is one terminology, saltation, that means the temporary suspension of the bed load. That means what I am trying to tell you, you see this grain, this is temporarily suspended here, then the water is not having enough capacity to keep it in suspension, the water is not having enough capacity, पानी के पास इतना कैपेसिटी नहीं है कि ये पूरा इसको सस्पेंशन में रखेगा. सो क्या करेगा, due to the gravity the grain again will fall, again it will be moving here, again it will fall. So this temporarily suspension, then traction mode, salt suspension mode, then traction mode, saltation mode, then traction mode. दिस प्रोसेस इज नोन एज सल्टेशन. मतलब थोड़ा ऊपर जाएगा, सस्पेंडेड होकर जाएगा कुछ डिस्टेंस, then that will again fall onto the river bed, then again it will be lifted, then again it will be falling down. So ये क्यों होता है, actually this is the thing. Suppose the grain is coming like this, it is getting impact here and it will be thrown like this, again it will be falling like this. So drop जब होगा यहाँ पे impact होगा, एक impact होगा तो ये रिवर्स इम्पैक्ट देगा, रिवर्स फोर्स में फिर से जंप करेगा, फिर आके लाइक यू जंप, ओके, like you are running. That is the example, best example for the suspension. The aeroplane is, sorry, the best example for the saltation. The aeroplane is flying, so that is the best example for the if the anything which is flying, the dust which is flying in the environment, you see na, that is the suspension. If you are throwing a rock which is going from your hand and it is again falling and again it is jumping and falling and going some distance, that is the saltation process. Okay, so this is the thing, and next class we will be going into the Joule-Ström's diagram. So for today this class is this much.